41
Yeah.
seconds.
All right. All right, I'm recording audio over here. Okay.
I'm
And I can
recording
edit it in my
visuals.
software. Okay, so I'm not going to go very fast with this just because I just want to at least chip away at it a little bit and kind of get to the punchline. All right, we're totally switching gears now. Okay, what we did at the beginning of the year, well, for the entire year, we dealt with the range of change functions. Okay, and we dealt with finding the tangent lines. Okay, the slopes on a particular curve. This is totally different now. We're doing a process called integration. And this is a big piece of Calc 2, all right? So you usually get a little kind of introduction to integration in Calc 1, and then in Calc 2, you just build on just integration, okay? And in fact, in Calc 2, you don't do too much, you don't do too many derivatives, okay? You do mostly integration. All right, so what does that mean, though? Well, we're gonna kind of start from the top here and try to imagine like what it is to integrate. All right, we're going to start off with a very, very simple model here. In order to avoid flood water entering your home, you rent a pump that can remove water at a rate of 500 gallons per hour for the first 8 hours of pumping. As the storm grew stronger, you got a second pump, and for the next 16 hours, you could remove 900 gallons per hour using 2 pumps. Okay, so let's graph that. Now, do you guys notice that this is a graph based on rates?
Okay.
Okay, so did you see this word right there? So this is actually a rate that we're going to call V of t. Okay. Now, this works, integration works, when you have a graph of V of t, and this is just t, time. So this would be the first derivative, right?
Okay.
This is the first derivative. Okay, but here's what's interesting. What if we wanted to know how much water was actually withdrawn from the what, basement?
Yeah.
It's just a home. Okay. Let's assume it's a basement. All right. So what we can do then is we can kind of go backwards. So for the first 8 hours, from 0 to 8, they actually were taking out 500 gallons. Okay. And it kept going. There's the second hour, third hour, fourth, fifth, sixth, seventh, eighth. Would you agree that that was a consistent rate? It's a machine, right? It's just going to pop. It's going to pull that much water out for 8 hours. Okay. What we're going to do is we're going to graph that. Okay. So then what happened is after that, they got another pump and they started doing 900 gallons up until the next 16. So they're going 900 for the next 16. All right, 16 plus 8 is 24.
Oh.
All right.
That is not how I
Okay.
took that.
Now does this make sense though?
Yeah.
Okay. All right, good. Okay, so 900, and the machines just kept breaking out until the next
Oh wait,
16,
no, I see it. I see it.
and then the pump shut off. Okay.
Mhm.
All right. So, what does the area under the curve represent? What is the area of these objects, by the way? What would it be?
No, base 900 times 16.
Yeah.
Height.
So what is it?
You want the total area?
What is the area of this first shape?
Oh, 500
8
times 8.
something.
8?
So 40.
Yeah, 4,000. Okay, let's write 8 times 500. Okay, and it's going to be 4,000. Ladies and gentlemen, what does 4,000 represent? Yeah. Gallons of water removed. Exactly. Okay. So what we've done here is by having the rate, okay, and we have the time, if we found the area of the rectangles underneath this, I'll call it curve, quote unquote, curve, okay, we have the water removed. So how much water was removed here?
14,400.
I'm sorry, one more. What did you multiply?
I multiplied 16 times 19.
Good. Okay, so great. You didn't
And I'm at
multiply
900.
24. You multiplied 16 times 900, right?
Yeah.
Great. Okay, and I'm sorry, say that one more time, Carly.
14,000 and then 400.
400. Okay. All right, so does that make sense that this represents how much water was pulled out, okay, from the pumps?
Yes.
So what we've got here is finding the area underneath the curve, okay, underneath this curve, which is really boxes. We actually were able to figure out the amount of water that was pulled out given a rate. We needed a rate, we had the time. When we calculated the area, we went backwards. We found the original function's area, okay, or the original function's value, okay. So what this represents is the amount of water pulled out of the house, okay. And so what we would do, what did we do in order to get the total area? Well, I'm sorry, what is the total, the total amount of water? Okay, I screwed up. Find the total area under for the total 24-hour period. So what does that mean? What does this represent? It represents the
18,000.
total amount of water, right? And we already said that. Okay. Okay. Now there's a trick, okay? Now Newton figured this out back in the late 1600s, but he did it very intuitively. Yes, ma'am.
How for like if I'm doing this on like a test, how is the equation explaining the meaning?
Yeah, like we don't really have an equation, do we? We just kind of have the situation, and we have these blocks that we could easily calculate the area of, you know?
Yeah.
So we don't actually have an equation just yet.
Okay, yeah, but like if you go down to C, how do I explain the meaning of in the context of the scenario?
Oh, okay. So this is the first 8 hours. This would be the second six. This would be the next 16. So the total area represents the total amount of water pulled out.
Okay.
Is that okay?
Yeah.
Okay. I know I said it, but I didn't write it down. Sorry, my brain is like trying to move quickly without doing. I'm trying to explain it verbally, but I'm not writing down much. My apologies. Okay. This stuff is not actually hard. It's just it's new, it's different, but I think you guys will find that it's kind of easy. Okay. In fact, I think the integration that we'll do for all of Chapter 6 is going to be pretty easy. Definitely not optimization, that's for sure. Okay. So, here's kind of the punchline. Okay. What we can do is if we have a rate of change function, okay, if you guys would underline that, okay, there's two big ideas in calculus are the tangent line problem and the area problem. And what's so amazing is that these guys are related. Now what you guys just saw was an example of the area problem, okay? The tangent line problem is when we were doing this, okay? And we did that for months and months and months. That's the tangent line problem. The area problem is what we just did, okay? So in the tangent line problem, you saw how the limit process could be applied to find the slope of the tangent line over smaller and smaller and smaller intervals as x or as h went to 0, okay, at any point on the curve. Now the second classic problem in calculus is finding the area under a curve, okay? So what this means is if you guys look at this picture right here, do you guys see that finding the area under the curve, how do we do that if we, like what's the equation for that? Okay, I can do boxes, I can do rectangles, it's length times width. I got the area for that. But like, what exactly is the height of this guy, and what exactly do I multiply it by going across this curve? Okay, and so Newton just kind of like had this idea called infinitesimals, and it worked, but he didn't like make it perfect. This guy Reimann made it perfect. Okay, So what he did is he kind of went under the hood and figured out exactly how this works. And so that's why these sums are named after him, even though Newton had a similar idea, okay? It just wasn't, he wasn't a mathematician. He was more of a scientist, physicist, okay? All right, so let's say, though, that you did have a 30-gallon. Okay, so what we're going to do is we're going to use rectangles now because we know how to calculate that area. We're going to use rectangles to get an estimate of that area under the curve, okay? So would you agree then that if I did calculate the area of this rectangle, couldn't that give me an estimate of what's under the curve? Yeah, okay, definitely give us an estimate. And then we would just keep going if we needed the whole domain from 0 to 8, okay? And then Reimann basically figured out is what we'll do is we'll make the rectangles smaller and smaller, okay? So that's the whole idea behind integration, is making very, very small rectangles underneath the curves, okay? And what's cool is you start off with rectangles and then they just keep getting smaller to a point where they are slivers, infinitesimally small slivers, okay? All right, so let's say we got this function and this is the rate, okay? It's the rate in which this 30-gallon aquarium is being filled with water, okay? So it looks like it's being filled with water slowly, but they keep dumping more and more water in. The rate gets up to about 6 gallons per minute. Okay, 6 gallons per minute. And then the whole process starts to slow down. Now, what are we going to find if we find the area of all of these rectangles?
How many gallons in total?
How many gallons of water got dumped into the aquarium? Exactly, okay? So that's what the area under the curve represents because we have a rate function, okay? So if we wanted to do this, we could actually figure out let's go from 0 to 5, okay? So what's the area of the first triangle?
2.
2 point something. Okay, do you guys recognize that we have to plug 1 in back into the function to figure out how tall that is? Okay, and I'm going to look at my answer key here. I'm going to open it up so that I got it here. Okay, let's make a table real quick.
It's only 1.
Okay, 1, 2, 3, 4, 5, 6, 7, 8. Then what we would do is we'd plug it in. So what would happen if I plugged in a 1? I get that height right there, right? Right here. Okay, so 1 goes into here. Bada bada bing. And I get 2.296. All right. So how many gallons were dumped in at that point? 2.296. Okay. Area total. All right. Does that make sense so far? I'm finding the area of this little rectangle right here, and that tells me how many gallons are actually dumped. Okay. Now, how about 2? How tall is this guy? Well, I don't want you to plug it in because of time. But if I plug it in, I get 4.243. Okay, so that's the decimal. How about the area total? Do you guys recognize that the area total?
No.
I grab the first rectangle and I add the second, right?
This is
Okay.
probably the 1 equation.
So 6 point something something. Okay. Let's just do. Is it okay if we just do a couple more?
Yeah.
Okay, you get the idea, right?
Yeah.
In fact, let's go all the way down to 8. Okay. This process is just going to continue. Okay. Oh no, I'm sorry. We go to 5, don't we? Just go to 5. At 5, it goes 5.543, but then that total reached 12.082. So the idea with integration is that not only are we going to calculate the area of the rectangles, but we're going to keep adding them up, okay, we're going to add them up. So this right here is an estimation of how much water was dumped in. But let me ask you then one final question with this example. What is it, an overestimation or an underestimation? What do you think, Tim?
Overestimation.
Why is that?
Just consider the rectangles exceed the.
Yeah, yeah. You can see that the rectangles are actually predominantly over the curve, aren't they?
Yeah.
Okay, but this guy's under. Okay, but that little space does not balance out all these spaces where it goes over. Okay. Yes, ma'am.
Couldn't we like, in the little thing like graph that you did, you know, like couldn't we just do like for each and then sum it up?
Yeah. Oh, yeah. For sure. Yep. You can do each of them, and then just add it all up. You don't have to add them as you go. That's exactly right. Okay? But here's the symbol for all of this process, ladies and gentlemen. As the rectangles get slower and slower, this right here, zoom in, this is the guy. That, ladies and gentlemen, is the indefinite integral. And what this would say is, this is the sum of all of our rectangles from 0 to 5, all of that sine equation. Okay? Now, do you guys see this dt attached?
Yeah.
That's part of the game. Okay? We're going to investigate why this works, but this basically is the height or the length times the width. Okay? The length times the width, and we're going from 0 to 5. Okay? That's the symbol going forward. Okay? So this is a very romantic moment right here. This is incredible. This is a big step. Okay? All right. Let's take another step. We got 10 minutes. All right. If this was really hard, I wouldn't be recording this. I would want to just have everybody present. But I think this isn't too bad. And what Reimann figured, okay, is that, you know, when Tim said you look at the rectangles, that's exactly what you do here. Do we agree? Is this an under or over?
Over.
That's underestimate, right?
Oh.
Okay.
Whoops.
And this is a
Over.
overestimate. Okay. And notice though, this is a left endpoint
That one's under.
Riemann sum. This is a right Riemann sum. In fact, I never say the word endpoint. I just say left sum and a right sum. Okay. Now, do you guys know? Oh, go ahead.
What do you mean with that?
Okay, great question. Now, do you guys see that? And this was kind of confusing to me when I first started this. Do you guys notice that I am looking for this rectangle? Do you guys see that I'm only using the left edge of the rectangle? You see how he's right there?
Mm-hmm.
Okay, that's the left edge. Okay, over here I'm using the right edge. Okay, now this is actually kind of easy, but I don't know if you guys noticed though, but from 0 to 1, I'm not gonna, do you guys see I actually have a rectangle, but he's flat. He's like right here, this is him. Okay, but because if I'm gonna touch the left part of the rectangle, he's at 0, he's completely flat. Okay, so we got a flat rectangle, we got this guy, this guy, this guy, we add them up, okay, and then we get an estimate. If we did the right side, we would get that overestimate. Okay, yes ma'am.
So if we're doing curves, I get it. Why we do the rectangles? But like, if it's a straight line.
If these guys are straight lines?
For example, the example 3, it's a straight line. You can calculate the specific formula, right?
Oh, I'm sorry, say that one more time.
For example, the example 3, you can calculate it with a specific formula, right?
It's so hard to hear because my 3D printer is going. Can you talk loud, like, in your manly voice?
The example number 3, you can calculate it with a specific formula.
Where's example 3?
Down.
Oh, okay.
You know what I mean? If it's a curve, I get it. Why you do the
Oh, got you. Okay, I know where you're going with this. Yes, you can use a formula to get it exactly.
Yeah.
Yeah. Oh, yeah, you could.
For example, if you're doing this, why would you do rectangles if you can do just a triangle? You know what I mean?
Yeah, in fact, you wouldn't have to. Yeah. Yeah, no, I totally get it. Why would you do it if you have straight lines? Yeah, you wouldn't have to. You'd find the areas, right? Add them up. So would you have to do like this guy? No. Okay, why would you do over and under estimates when you can figure that out? I totally agree with you. You wouldn't do it. But not everything is going to be a straight line, so we're kind of building towards breaking away from that. Okay, but yeah, I totally understand what you're saying. In fact, when we do this guy, we're going to figure out his exact area. We're not going to have over and under. We could. Okay. All right. So, here we go, ladies and gentlemen. All right, let's take a look at this guy right here. All right, now this looks so fancy, okay? And it looks like there's profanity right there in the middle of it, which is kind of hilarious. But we don't ever want to use this. We like this guy. This guy's more friendly, okay? But what I want you to kind of understand, this is what makes Newton's work, okay? Newton came up with basically this, okay? But Reimann figured out, like, here's why it works, okay? Now what he did, okay, this is the punchline. He's basically saying, if I calculate the height, if I calculate the height of the curve, magic moment.
We
All
should
right.
have put a dad on our t-shirts.
What's that? It's too late now. They're already being made. Yeah. Okay.
Wait, what is the color?
Black.
Hey, you guys. You good.
I had the same reaction.
I just went with the color you guys voted the most. Sorry. They should be here by the time we have the escape room too. All right. So, okay, I got to move on to the next square word. This is the height. That's the width of the rectangle. Okay. Now what'll happen is the length times the height gives you the height of one rectangle. What does this do?
Tell you it.
Adds them all up. Okay. What does this guy do?
Be a limit.
Gives you the limitations. Like it
Yeah.
can only be from here to here.
Yeah, it can only be from here to here. So the idea here is that this n, okay, we're going to take so many rectangles. This is 4 rectangles, right? What if I had 1,000 rectangles? Would I be closer?
Yes.
Oh yeah, I'd be really close, okay? In fact, what I'm 3D printing an example, okay? A physical example of why we're going to get closer and closer and closer to the actual value, okay? So this guy says, Reimann figured out, if I take the limit of an infinitely number of rectangles, okay, and add them up, I'm going to get this guy, okay? And it was brilliant. It was absolutely brilliant that you could add infinitely many rectangles in a mathematical process. It seems impossible. It seems like you'd be at your calculator for years just to do one of them, but in fact, it works beautifully, okay? So, when we got here, what we're going to get here is we're going to go ahead and play around under the hood of working with lower and upper sums. We're going to work with left and right sums so we can get closer and closer approximations, okay? All right, so what you do is you draw a graph of the function over the interval, okay? And I know we only got a couple more minutes. We're going to figure out how many rectangles, the width, okay? This is the width. Can you guys write that in? That's the width. You figure out the width of your rectangle. Then you figure out, compute the x coordinates of the rectangle, okay? We compute the areas. Compute x coordinates of rectangles either right or left. Compute the areas, okay? So this means you figure out the heights, okay? Then we compute the areas. They're either inside, being an underestimate, or they're an overestimate, okay? So would you guys write that in? Inscribed means it'll be inside the function, and circumscribed means to be slightly outside the function, okay? Then what we do is we add them all up, okay? No, and I'm glad you asked that question, Sophia. Like, why would we do that if we can actually figure out the area of this guy, right? Isn't this a trapezoid?
Yeah.
You could look up the formula of a trapezoid and find the area under the curve. Totally understand, okay? I mean, why? Why would we do this is just practice, okay? We're going to practice what it means to have that left and right, okay? So first of all, we have the area under the curve here, and we have the equation. Let's just draw up. You guys need colored pencils for this one, okay? But we don't have enough time,
Yeah.
okay? So we're going to stop right there,
Ah.
okay?